Okay, so today's our third topic. We're going to talk about the periodic table. Last class we learned about a ton of different scientists, from John Dalton to Niels Bohr. One of the ones that I need you to know a little bit about is Dmitry Mendeleev. And I think the story behind Dmitry Mendeleev is super cool. Right? I mean, basically he had this idea where he's got all these elements that scientists are starting to discover, and he starts to write down properties of them. He starts to record some similarities that he can find. And he discovers that as he starts to match them up, he starts to put them into groups and rows, and he kind of like rearranges them. And he begins to make the modern periodic table. That's our focus today. I need to be able to make sure that you guys understand how to use a periodic table, how to find information on it, what it refers to, what it means, so that we can go from there. And I love this first slide because it's kind of a visual of all of the elements on the periodic table. Are elements the smallest thing that exists? No. We actually learned that for a while they thought the elements were the smallest building blocks of life. Democritus had this idea of atomos, atoms being indivisible. We've since discovered that there are subatomic particles, the protons, neutrons, and electrons. But for right now, the periodic table is more or less the smallest thing we're going to discuss. And like I said, Mendeleev found a way to put them into groups and organize them. And I like this section right here. I'm going to highlight it on the board, just for anybody who watches a video later. Let's put a pen on here. I like this section right here, because I think this illustrates exactly what Mendeleev was doing. He discovered that neon, helium, argon, and krypton and xenon, they all had a really similar property. Here's that property. They're all gases, but more than just being gases, they're gases such that when you run electrical current through them, they glow a cool color. Can I say that again? All 5 of these things right here that all go in this up and down column, they all have the same property of being both gases, and when you run electricity through them, they glow a certain color. You might actually recognize some of these things. They've actually, on this interactive table here, drawn them all as like flashing neon lights. You guys have heard of neon lights before, right? Neon is actually one of the ones on the list. The problem is that sometimes we use the word neon light, and it's not actually made out of neon. We could call it a neon light, but it's actually krypton. That's the gas that's being used. Or it could be helium, that's the gas that's being used. But yeah, all of these things right here, they make those really cool, kind of like night kind of lights that you might find on like a store sign. Does that make sense? That was the essence of what Mendeleev was trying to do, is trying to organize these things in the periodic table. Okay. So our basic periodic table then contains all of our elements. Okay. There are 100 plus elements that we know about on the periodic table, and we're constantly trying to discover if there are any more. Okay. The first thing I need you to know is that there are 90 naturally occurring elements, and then 25 synthetic ones. That's the first place we're going to start. The question then is, how in the world am I going to know which one is natural versus synthetic? What even is the difference? Okay. I'm going to go sit over here by this periodic table, and I really hope you can see what I want to point out here. I'm so sorry if you can't. We'll have to chat later. I want to focus on this element right here, technetium. It's number 43. Can I sit here? Is that going to work? Can you guys see this one where it's at right here? This is a really good case study to discuss. What is unique about technetium based on what you can see from where you're at compared to everything else around it? Yeah, there's actually 2 things. One is the radioactive symbol right here. And then what else is weird about it? The lettering is black. Does that make sense? Okay. On this particular periodic table, the black lettering with the radioactive symbol, that's more or less the giveaway for something that is synthetic. Here's what synthetic means. It means that it doesn't naturally occur on its own. It is the byproduct, generally, of nuclear waste. You guys have heard of nuclear reactions before, where you use uranium or plutonium, and they make a nuclear reactor for electricity, right? Well, what ends up happening is after that process is over, one element actually changes from something to something else. The most common radioactive materials are either uranium or plutonium. And usually what happens is uranium then turns into this, which turns into this, which turns into this, which turns into this. And slowly through a long process, maybe you've heard this phrase before, nuclear decay. Okay. I don't need you to know the nuclear physics on day 3 of chemistry. That's a little much. I'm trying to give you the Cliff Notes version. But through the process of nuclear decay, you can eventually make technetium. But you can't mine it in the ground. And when you do eventually make this technetium, It's radioactive and it's very dangerous, so that's the sort of thing that you would want to put in like a big steel drum and probably bury in a mine. So long story short, all of the elements that are black on here, you guys can see these ones right here, especially this one. That one's the really good test case. They're all synthetic. They're all the byproduct of a nuclear decay. The rest of them are naturally occurring, which means you can find them without having to do some sort of nuclear reaction to them. The question then becomes, how in the world am I going to figure out on a periodic table which one is which? And the key is to look for little brackets around a certain number. Okay? I know not all of you have a periodic table nearby, but if you could find, like, say, hydrogen on a periodic table, hydrogen is number 1, and sometimes there's a 1.01 written on there. Over here would be helium, and it's written as 4.00. Okay? If it's got like a 2 decimal number to it, it's probably naturally occurring. Technetium, I believe if you have a periodic table, gives you a number on there in brackets, and I believe technetium is number 43. Long story short, if you ever see some brackets around a number, that can be the giveaway that it's synthetic. Okay. Most of the synthetic elements are actually the ones that are like down in those bottom rows, though. Does that make sense? Next time you have a periodic table nearby, I don't know whether you want to print your own or if you're going to use yours off your phone, but take a look for that. Look for the bracket thing. It'll tell you which one is synthetic or not. Wait, here's some more properties of metals. As Mendeleev was putting his periodic table together, we often now call this the staircase line. The staircase line, if you're looking at this table over here, kind of goes right here around these pink elements. This table is really nice because it's got a nice bit of color to it. I'm going to try to find a different periodic table on here and try to draw in the staircase line. You can actually see it right here. It goes here, there, there, there. It kind of basically walks down. Hopefully you're familiar with this. The long story short about it is that anything on this side of the staircase line is called a metal. And anything on this side of the staircase line over here is called a non-metal. Okay, first thing I need to point out about that. Metals and non-metals are not synonyms, or they're not part of the same classification system as solids, liquids, and gases. A lot of students think that metal means solid, but that's not necessarily true. As an example, mercury is on the metal side of a periodic table. Mercury is actually a liquid. Okay. Carbon is actually on the non-metal side of the periodic table, and it's usually a solid. So don't think that metal means solid and vice versa. Okay? Here's what metal refers to. It's all about properties. Oh, did I go too far? I did. All of the metals have very similar properties. Like, metals are usually strong. They're usually durable. Anybody ever heard this word before? Malleable. Do you know what it means? Yeah, it's flexible enough that you can bend it in like a sheet of metal. The example I gave to my first block class was, imagine that you're designing a car and that you have like a big sheet of aluminum that you're going to use as like a side panel. If you have the ability to like bend it and shape it in that sort of way, it's malleable. If it is so rigid that if you tried to bend it, it can't bend at all, or it snaps in half, it's not malleable. Another example, spaghetti. Uncooked, spaghetti is not malleable. You try to bend a strand of spaghetti uncooked, it's going to snap. Does that make sense? Cooked, however, spaghetti is all of a sudden flexible, and now you can bend it around. Okay, so that's what malleable refers to. The other word that kids sometimes aren't as familiar with is the word ductile. Anybody know what ductile means? Take it. It's similar to that, but that's actually a different property entirely. You want to take a stab at it? You're very close, though. It's similar to electricity. You might actually notice, though, that electricity is actually written on this list as its own property. Okay, here's why it's similar. Ductile means you can make a wire out of it. Okay. Anybody ever cut open like a wire? Wires are braided. There are like thin strands, and like usually the thicker the wire, the more braids of wire there are there. That's ductility. If you can make a wire out of it somehow, it's ductile. So it's why you're close, because it's similar to electricity, because it's often used. I would then say that generally, if it's ductile, it probably can conduct electricity, right? But they actually describe two different things. Can you make a wire out of it? So those are your metals. On the opposite side of the periodic table are your non-metals. And so if I go back to this table up here, that's everything more or less up in this corner over here. Now, in general, these things here are gases and liquids. But again, don't go thinking that these things over here are not solid, because carbon, phosphorus, sulfur, selenium, iodide, and astatine, they're all solids but considered nonmetals. Okay. Let me give you the example again of carbon. If you're writing with a pencil, the lead, quote unquote, that you're using as your pencil is actually not lead, it's actually carbon, it's graphite. Do you think that that lead in your pencil there would make a very good wire? Well, no. I mean, as you rub it on the sheet of paper, it like disintegrates and falls apart, right? So even though it is in a solid form, it definitely doesn't have strength. It's definitely not very hard in that sort of way, right? It wouldn't probably conduct electricity. So the nonmetals basically then are everything that's opposite properties. Okay. The weird ones are the metalloids. The metalloids are the ones that fall right along the staircase. So let me go back to this slide right here. Everything that's right along the staircase, there's a few of these that actually have the properties of both sometimes. If I were to use the word like a tweener, something that's like in between, that probably fits well, where sometimes they're metal, sometimes they're non-metal. Let me give you an example. Silicon. Okay. Silicon is actually quite flexible, and so I could probably describe silicon as being malleable. Malleable is a property of metals. However, silicon does not conduct electricity or heat. We often use silicon to make like oven mitts out of. Anybody have like silicon oven mitts at home perhaps? Right? It's kind of like a plasticky sort of material. It does not conduct heat. So it's got one property that fits metals, but it's got one property that fits nonmetals. So we call those metalloids. There are 7 known metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. I don't need you to memorize these. Okay. You can always look this information up. I mean, it's not a bad idea to write it down on a periodic table at some point, but you don't need to memorize that. Okay, now there's a few other ways that we record how the periodic table works. One is columns that go up and down. I've already described this with the idea of the noble gases. That's actually the name that we give to everything in group 18. If I could just draw a rough periodic table here. Here's just like a really rough periodic table. It'll look something like this. Remember all these ones over here that were like the neon lights? They're all part of the same group because they have very similar properties to them. Okay? And basically that's the name we give to anything that goes up and down. There are 18 groups on the periodic table, and some of them get a special name. Group 18, way over here, we call them the noble gases. Group 17 is called the halogens. Groups 1 and 2, over here as we kind of start the periodic table, 1 and 2, they have names of alkali and alkaline earth metals. Okay. The key thing you need to know about these guys, it's all about the similar properties. Okay. That's how it was organized. Okay. Now, if groups go up and down in columns, then periods go side by side. Okay. And this is where the periodic table, there's a little bit of an intricacy I need to make sure you're all aware of. There are only 7 rows in the periodic table, which confuses people because they look at the table and they go, Chris, there's 9. Why can't you count? Right? Here's a classic periodic table, right? Look, there's row 1, 2, 3, 4, 5, 6, 7. They're like 8, 9. That's not actually how it works. And I like this table over here because they drew some nice arrows there. I don't know if you can see this here. But here's row 1, 2, 3, 4, 5, 6, 7. And these guys right here don't have numbers. Because you can see there's a little orange arrow that kind of drops down here and a little red arrow that drops down here. As a space-saving maneuver, rather than making it go 55, 56, 57, and all be like in a row, the table would have been like twice as long if it wasn't for this. What they've done is they've cut out a whole section of these guys right here, cut them out and dropped them down below. So if you're actually counting them by number, it goes like from here to here, here's 37, 38, 39, 40, 53, 54, 55, 56. It drops down to here and then comes back along here. So there's actually only 7 rows in the periodic table, and we call those periods. Okay. They don't really have anything special in common. We will talk about that again in a bit, though, as to why there specifically are 7. Do you guys have any questions so far? Hopefully this is somewhat review, so I'll keep moving on, but do stop me if you have a question. Okay, this is something that may be new to you. It's called an allotrope. Whenever we're talking about elements on the periodic table, you need to know what allotrope you're using. Let me give you an analogy from everyday life that I think helps. Imagine that you need to go buy a toothbrush. Okay? Now, if you go to Costco, you might be forced to buy like a 20-pack of toothbrushes because you buy it in bulk, right? But if you were to go to, say, I don't know, Shoppers Drug Mart down the street there, You could go and buy one toothbrush. It might cost you $3. But you could buy like a 2-pack of toothbrushes and it might cost you $4. Or you could buy a 4-pack of toothbrushes and it might cost you $6. Does that make sense what I'm getting at here? Elements work the exact same way. Some elements, you can only ever buy one of them. Right here, sodium is a good example. Sodium only comes in groups of one. It's like you have to buy one toothbrush. But there are some things that come in different groupings. For example, nitrogen or bromine or fluorine, those things have a little 2 in the corner. It means that they come in always in that package of 2. Sulfur, you have to buy in 8s. Arsenic, you have to buy in 4s. Allotropes are really frustrating then because you kind of just have to memorize and know some of the common ones. I'm not going to make you guys memorize these. Like, you're more than welcome to go back to this slide right here and kind of look it up again if you ever kind of forget what common allotropes are. As a good case study, let's focus on oxygen, which is letter O. Oxygen is never just a single O. It's either O2 or, on rare occasion, it's O3. O2 is the oxygen gas that you and I are breathing in right now. But oxygen can actually come in a 3-pack, a triplet, and it's found in the ozone layer. You guys heard of the ozone layer? Right? It's supposed to filter out UV rays. O3 is another allotrope of oxygen. One of the really cool case studies is carbon. This is a slide that talks about carbon. All of these things on this slide are different allotropes of carbon. Diamond is made out of carbon, pure carbon. So is the graphite in your pencil. So would just generic soot. You know, like, say you go camping and there's a fire and you see the remnants of the fire and there's just some soot left over. That's carbon as well. All of these things are considered to be carbon. But this soot right here could be carbon in a 1-pack. This graphite right here could be carbon in a 4-pack. And this diamond right here could be carbon in a 40-pack. I like this slide because I think this slide really helps to illustrate what I'm going for. These are all allotropes of carbon. And you know how I gave you that Costco analogy earlier? Some of the allotropes of carbon are really the Costco pack. This is some sort of carbon that maybe comes as like carbon 20. This is maybe carbon that comes as carbon 40. And this guy right here, this is a carbon nanotube, by the way. This could be like carbon coming in like a 200 pack. This is like you're going for bulk at Costco, right? So, long story short, when it comes to talking about your elements, all elements have an allotrope, which means that in the bottom corner down here, it tells you how many of them come in a grouping. Do you have to buy 1 at a time or 2 at a time or 10 at a time or 100 at a time? Now, we're going to talk about this word a little bit later. I spelt this wrong, by the way. I noticed this first class. It's not called isotropes. It's called isotopes. But these are 2 words that kids often get confused. Allotrope is what I just talked about. It's the different number of atoms that group together while being of the same type of element. Isotope is a different thing entirely. I'm going to do that on a future slide if that's okay. But do try to get those 2 words. Don't use them interchangeably. They're not synonyms. This is another cool slide. Both diamond and graphite are carbon. Pure carbon, 100% carbon. But based on how many of them there are, changes its properties. This is diamond right here. Incredibly valuable, worth lots of money. And if I look at this box right here, it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Maybe there's 16 carbons in that particular one right here. Whereas the way that graphite, which works in your pencil, works is each of these edges right here would be a carbon. And so even though they're both pure carbon, based on how you like arrange them, they have completely different properties. Kind of cool. Okay, let's move on. So here's what we're going to do for the rest of our class. We're going to really focus on atoms and what's inside of an atom. Based on Ernest Rutherford's experiment, we now know that atoms consist of subatomic particles. Prior to that, the theory was that an atom was as small as it gets. But we now know that inside of an atom, there's really a couple of different things. Let's stand here so I'm not in your way. Inside the atom is something known as a nucleus. And we believe the nucleus is really, really dense, really compacted. And inside the nucleus are your protons and your neutrons. And I usually write those in a shorthand notation of P+ for protons and N0 for neutrons. We believe that inside the nucleus are those neutrons. Around the nucleus, somewhere around them, are electrons. I'll write those as E negatives. Now, this is actually a really primitive picture of where we think the electrons are. We actually believe now that electrons exist in clouds in the quantum model, but for right now, this is not a bad picture because it kind of gives you the visual of right in here, there's a nice condensed nucleus, and then floating around it somewhere are the electrons. Okay. So I talked about isotopes a little while ago. Why don't I focus on that right now? Hopefully you're somewhat familiar with this concept. Let's say that I were to talk about hydrogen, and I were to ask you, what is hydrogen made of? Well, there's three parts to it. The first part is whether or not it has any protons. The second part is to whether it has any neutrons. The third part is to whether it has any electrons. I'm going to ditch electrons just for now. We will talk about that in a sec, but let's just focus on protons and neutrons. Hydrogen on the periodic table is number 1. Because hydrogen is number 1, it has to have 1 proton. But how many neutrons does it have to have? You know what? It can have any number of neutrons. There's really no rule behind how many neutrons it has. So it could have 0 neutrons. Or you could have a hydrogen that has 1 proton and 1 neutron. Or you could have a hydrogen that has 1 proton and 2 neutrons. The only thing that makes it hydrogen is that it has to have 1 proton. As soon as you change how many protons it has, you call it something different. These are known as the isotopes. And here's how we would describe them. The hydrogen isotope that I've just listed right here, we would write it like this. It would be hydrogen. We would put a 1 down in the bottom corner. That 1 in the bottom corner is called its atomic number. And it refers to how many protons it has. So I guarantee you, hydrogen has a little 1 in the corner. Half the time we don't even write it, because it's just kind of implied it has to be number 1 if it's hydrogen. As a different example, oxygen is number 8 on your periodic table. We wouldn't necessarily even write the 8 though, because it has to be an 8 if it's oxygen. Sometimes in this top corner right here though, we write something called the mass number. Mass number. And the mass number tells you what's in the nucleus. And all it does is it tells you how many things are in the nucleus. So if we have, say, this first one right here that I've highlighted, hydrogen that has 1 proton and no neutrons, how many things are in the nucleus? 1. That 1 proton. So you do a little 1 up here in the corner. And that's known as an isotope of hydrogen. We would write it something like this. I'll write it a little bit neater. There's hydrogen 1, 1. You may even see it written like this. Hydrogen 1. But that's not the only isotope of hydrogen that exists. There's also something known as hydrogen 2. Hydrogen 2, you'd still write H for hydrogen. You'd still put a little 1 down in the corner right here, but you'd put a 2 up here. Hydrogen 2 is this one right here. I'll use a circle, where there's 1 proton and 1 neutron. 1 plus 1 adds up to 2, yeah. The basic logic is that if I ever give you a notation that looks like this, I'll just do a random element, and let's go with 10 and 5. I don't even know what it is, but I can tell you this. It has 10 things in the nucleus. It has 5 protons. So what's 10 minus 5? 5. There must be 5 neutrons. The fast way of doing this is that if you take these two numbers right here and subtract them, it tells you how many neutrons there are. So that's known as an isotope. Isotopes and allotropes are similar but different. Allotropes tell you what grouping they come in, and whenever you do an allotrope, it means you're going to put like a little 2 in the corner right here, and it tells you that you always need to have 2 of a hydrogen. This corner right here is defaulted to the atomic number, which is protons, and the top corner over here is defaulted to how many total particles there are in the nucleus, which is always protons plus neutrons. Let's try a little activity, just a little brief aside. I'm going to play like a guess who game. I'll sit down, I think, for this. Tell me who these isotopes are. Who is this? Okay, let's say you have 5 protons, 7 neutrons. Let's say you have 14 protons, 12 neutrons. And let's say you have 2 protons and 1 neutron. You need a periodic table, so this may be a little bit unfair for me to throw this at you here. So if you don't have a periodic table, you have to try to look at this one as best you can. Let's do the first one here. The first one, 5 protons, 7 neutrons. You just got to find who number 5 is. So here's 1, 2, 3, 4, 5. Okay, so it's boron. So we would write this then as boron, B. Now we might write the 5 in the corner. You don't have to because it has to be boron. What number do you write up here in this corner here? 12. The reason why I put a 12 here is because that's what 5 plus 7 equals. That's it. We would call this boron 5, or sorry, boron 12. We would never call it boron 5 because it's always number 5, but you could call it boron 12. Let's try another one here. 14 and 12. Number 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Silicon. So I'm going to shorten this one up a little bit here. I'm just going to call it silicon. And then I'm going to call it silicon 26. The 26 because there's 14 and 12, so it adds up to 26 total. If you want to, you could write it like this, silicon with the 26 in the corner. And if you'd like to, you can write the 14 here. And if you'd really like to, you could tell me how many groupings silicon comes in as well. All 4 corners of the symbol mean something different. Sometimes we skip this little corner. We don't have to use it. And I haven't even talked about this corner here yet because there's something for that corner too. Let's try one more. 2 protons, 1 neutron. Find a periodic table wherever it is you want to get one from. Here's 1. There's 2. So it's helium. Helium what though? Helium 3. Is there such a thing as a helium 4? Sure. You know what helium 4 is made out of? 2 protons, 2 neutrons, that's all. The analogy I give for neutrons is that they're kind of like the extra weight, the extra fat in a molecule or an atom in a way. It doesn't change who it is. Like the 2 protons or the 14 protons, it's what defines the atom. You can have as many neutrons or as few as you want. It just means you have a skinnier or a heavier isotope, that's all. So neutrons are kind of like the extra weight to a molecule. Does anybody have any questions on that? Okay. So the last thing we need to talk about then is putting it all together. We need to talk about the subatomic parts, protons, neutrons, and electrons. I've just discussed with you the idea of neutrons and protons, but the final thing is, well, what about those electrons? So here's some vocabulary we need to know. It's the word atom versus ion. Atoms are neutral. And so what happens if you ever have an atom of something, however many protons you have has to equal how many electrons you have. If I have a hydrogen atom, you have 1 proton, 1 electron. If you have a neon atom, you have 10 protons, 10 electrons. But you don't have to. Those can change. One of the best ways for us to illustrate the electrons is to use this model right here. We often call this a Bohr model of the atom because it shows the electrons in those like rings or energy levels. That's not what we think they do. We think they live in those cloud bubbles, but this works. There's a bit of a pattern to it. It actually helps explain the periodic table. Each one of these rows or periods in the periodic table actually corresponds to a ring in this model right here. And in a way, I like to think of them like a hotel, where the first ring is floor number 1. The first level, the first floor, holds 2 electrons. Look at this oxygen atom right here. It's got 2 electrons out of 2. It's filled up its first ring. So level 1 is full. Well, you need more room, so go up to the second floor. The second floor always holds 8. And you might notice on the periodic table, the first row has 1, 2. The second row has 1, 2, 3, 4, 5, 6, 7, 8. So the second row has a max capacity of 8. Is this atom right here using its max capacity yet? Count the outermost ring. There's 1, 2, 3, 4, 5, 6. It's only at 6 out of 8. Now look at oxygen on the periodic table. It's filled up 1, 2, that's the first row. And then the next row it fills up 1, 2, 3, 4, 5, 6, 7, 8. As soon as you would have filled that far, would mean start a new row. Let me try the next example here, magnesium. The first row is always out of 2. So the first energy level is filled 2 out of 2. The second energy level is always out of 8. Is this one filled up? Yeah, look, there's 1, 2, 3, 4, 5, 6, 7, 8. The second level is 8 out of 8. which means that this atom is getting so full of electrons it needs to open up the third, I don't know, the third level up, right? The third floor. I feel like the hotel room analogy. The third floor is also out of 8. Is it full out of 8? Now look at this ring right here. There's only 2 out of 8 filled. Right? Which kind of explains why magnesium goes right here. It's only the second one over. Okay? That's kind of how the electrons work a little bit, is they fill these, we call them orbitals. This is a good picture of what we think they would look like, just to help explain it, but that's not actually what we think they really look like. Okay. Now, the word we give to those electrons then is called a valence electrons. And the outside-most electrons we call valence electrons. They're really key in terms of forming bonds. I'm not going to read much off my slide. I just want to point something out here. Valence electrons can help us figure out whether or not an ion is going to be formed. That's a key word I need you to know. An atom is neutral. Atoms have equal protons to electrons. But ions don't. Ions means that there's more positives or negatives in an element. And that's where we're going to finish here. I actually found with our first class that it worked better if we just skip right to the end slide. I've got a bunch in here that I can come back to. But if any of you are following along with notes, why don't we go to this very, very last slide right here? And I'm going to try this right now and see if this helps. We're going to play that exact same game that we just did a little while ago, where I'm going to tell you how many protons, neutrons, and electrons something has. But now we're going to add on the electrons, because we didn't do electrons last time. Okay. Anytime that you have any random symbol, there's 4 locations that we may have to include. This location right here is how many protons there are. It's called the atomic number. This location up here is how many total particles are in the nucleus. It's known as the mass number. This corner right here is reserved for what the isotope is. Sorry, not isotope, allotrope. I just did it wrong. And so that's like where it has like a 2 or 3 pack of something. This final corner right here is the one I skipped. This tells you whether there's a charge to it or not. And so if there's a charge to it, then we'll add like a +1 or a +2 or something like that. So let's give one a try, because I think you guys are ready for this. So there's 17 protons, 20 neutrons, 18 electrons. Question number 1, who has 17 protons? Hey Google, what's atomic number 17? This is really long. There you go. That was really long. If you guys have a periodic table, that'd be faster though, right? So, because it has 17 protons, it's chlorine. Now, if I want to start filling out the corners of this, I could put a 17 down here in the corner, but just be aware that's optional, because like, it has to be chlorine. It's the only option. What number should go up here in the top corner then? What number should go in the top corner here? Yeah, you're right. It should be 37. Now, some kids think it should be 20. But it's 37 because it's the total number of things that are in the nucleus, which is protons plus neutrons. So if you just add those two numbers together in your head, 17 and 20 gives 37. This is known as a chlorine 37. Okay? It could be a chlorine 36, a chlorine 35. This just tells you how heavy it is. Is there extra mass due to neutrons? Okay. Now, we can, if we would like to, in the bottom corner, put a little 2 here because chlorine normally comes in 2s. I don't really need to right now, but that's what we would put in the corner here. This corner right here, though, is going to tell us our charge. Look at protons versus electrons. Can you guys all see how there's one more electron than there is protons? It means that this is no longer an atom. It is an ion. It is a 1 negative. So sorry that writing is kind of on top, but the 3 corners we would use probably would be this. 17 for chlorine, 37 for its total weight, and there's a -1 charge. If I were to put this into words, I would call it a chlorine 37 1 minus ion. That's how I would describe this combination of subatomic particles. 17 protons dictates that it's chlorine. It has to be. The 37 is because these two things add up to 37. And then by looking at the disbalance between electrons and protons, that tells us the charge. Let me try a couple more with you, and then I'll let you try some. Sorry, it's getting a little messy on here. All right, 10 protons, 11 neutrons, 10 electrons. Hey, Google, what's atomic number 10? Neon, N-E for neon. By the way, it would help if you had a periodic table somehow nearby, whether you print it yourself or whether you find a digital copy on your phone. Albert Einstein once said, never memorize anything you can look up in books. I think that's a really good quote. If I can ask my Google Home Mini the answer to the question, don't worry about memorizing it. Right? Well, but I don't think you can ask it everything. Hey, Google, what were the causes of World War II? I'm just curious what it will say. Oh, it's actually going to try to answer it. I asked for World War II, though. Yeah, so you give me the wrong answer. I don't know that you can ask Google everything and have it be correct. Is that fair to say? Because I said World War II, didn't I? And it gave me World War I. So I don't know that it can do everything. But look, if you can ask Google a really simple question like how many protons are in something, I don't think you need to memorize that. So anyways, since Albert Einstein thinks you never have to memorize things you can look up in books, I have that same sort of rule. Guys, we're not going to write tests in the same sort of way you're used to. So don't stress out and be like, I got to memorize all this stuff. That's not how we're going to run this class. All right, anyways, I got a topic. Neon's number 10. We can put a 10 in the corner. The number that goes up here will be 21. Why is it 21? Well, because 10 plus 11 adds up to 21. So its total weight is 21. Because there are equal numbers of protons to electrons, this is neutral. I'm not going to write anything else. We're going to leave it. And I would call this, if I had to put it into words, a neon 21 atom. The word atom implies that it's neutral. Okay. One more, then you guys will try the last two. 7 protons. Yeah, go ahead. Yeah, it's positives in island 2. Yeah, good question. Cool. Okay. Hey, Google. What's atomic number 7? Wow. It's nitrogen. That was a pretty bad answer there, Google, wasn't it? It's nitrogen, just so you guys are aware. Nitrogen is N. Now, I'm going to not write the 7 in the corner because I don't really need to. We could just write a 15 up in the top corner here and call it good. This is the nitrogen 15 atom. And hopefully you figured out why it's an atom, because electron and protons are the same. I could write the little 7 in the corner, but often we skip that because doesn't that have to be 7 because it's nitrogen? Okay, take a couple of minutes here, just think through in your head or write down what you think the last 2 are. We'll talk about those, and then if we're good, maybe we'll wrap up and we'll do a bit of a review. So try the last 2 here, see if you can answer those. Ooh. I don't know. Someone got in the way of that one. A what crane? A walking crane. That's bad. There's a question over there. Val, is it right? How can I help? For which corner? Right, this one right here? Because there was one more or you're doing this random one I removed right here, hey?
Yeah, the one that was on the book.
Oh, sorry, that's 18 up here. Oh. Sorry, my mess has gotten in the way here.
Yeah, that makes more sense.
Yeah. Yeah. Can you see that? Because it's 17 right here, and right there's 18. So because of 17 to 18, it's a 1 minus charge. Based on what you have written here, if it was 14 and 18, I would give you a 4 minus charge. Does that make sense? What did you ask? Hey, Google, stop. Okay, here. Here's the answers. Okay. Okay, here's the answers to the ones we did. Let's talk through them here. There's 7 protons. Because there's 7 protons, it has to be nitrogen. Hopefully you can read my writing here. Shh. Stay with me. So it has to be nitrogen. Now adding protons and neutrons, 7 and 9 in both cases adds up to 16, so it has to be a 16. However, if you can see here, there's 7 and 7. I don't care whether it's a million and a million or 2 and 2. If these two numbers are the same as each other, it's an atom. It's neutral. All you care about is the disparity or discrepancy between protons and electrons. So since here there's 7 protons versus 8 electrons, there's 1 more electron, so there's a -1 charge to it, and we call it an ion. Let me go back to some of the slides I skipped now, because I think now that I've shown you our end goal for the class, now I can go over some of the stuff that I kind of glossed over a bit. We actually have some more vocabulary that we can use to describe some of these things. Let's say that you make these ions, where there's a discrepancy between protons and electrons. This is a really good slide to talk about here. Take sodium. Sodium as an atom should be 11 versus 11. Sodium is number 11 on the periodic table, so it has to have 11 protons, and as an atom it has 11 electrons. But let's say that for some reason it doesn't have 11 electrons. Let's say that it loses 1. Well, then it would be 11 and 10. In this example here, there's more positives than there are negatives, and so this becomes a sodium positive charge. We have a name we give for anything that's positive. We don't just call it an ion, we call it a cation. And I have a really silly way of remembering which one is which. Cats have paws. It's dumb, but it works. Cats have paws. You know, like kitty cats have paws, which means that a cation is positive. Catch that? Cations are positive. Yeah, it is, yeah. It's deep. Okay, the alternate possibility, we call it an anion. Anions are negative. So anions are the situation where there were, say, supposed to be 17 with 17. They're equal to each other. This would have been an atom. Say there's an extra electron somehow. So it's not a 17-17, but now it's 17-18. If there's 1 extra electron, we put the negative up in the corner. We often don't write the 1, by the way. We could write it as chlorine 1 negative, but we usually just write it as chlorine negative. We usually don't bother writing 1s. Okay. The name we give for that then is anions. Anions have more negatives than positives. Cations have more positives than negatives. Okay. So that's one of the slides I skipped over just for terminology. This is a slide right here that just kind of rediscusses the idea of atoms versus ions. The only difference then is whether or not you put a little charge up in this corner. Atoms never get a charge in the corner. Ions get a plus or a minus. So that's a slide I skipped over there. By the way, I hate reading off of slides. I think it's really poor for me to stand in front of the class and just literally read to you. Atoms have the same number of protons in their neutrons. The nucleus is like, I think it's really dumb for me to read that. So I will skip over slides once in a while if I don't think it's purposeful, because you guys can read this yourself if you need to. Here's a picture that kind of illustrates how the electron system works. Hydrogen has 1 proton, therefore 1 electron, 1 dot. Helium has 2 protons, therefore 2 electrons, 2 dots. When does the first level get full? At 2. So once you fill the first level of 2, lithium has 3 protons, should have 3 electrons. But rather than drawing it like this, lithium with dot, 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 the first level, its capacity is 2, right? Like the first floor of the hotel only has room for 2, right? So that's why the first ring has 2, and then the next one has 1. Okay. So that's another visual you can use to describe. I think that's one of the slides I ended on. So I think maybe we'll call it a day here. You guys can read the rest if you'd like to, because most of it's just written notes. Okay, let me give a quick summary, and I'm going to give you guys some time to work on your reflection piece. You're even welcome to use this as part of your own summary that you can write back to me. I think we've really accomplished 2 things today. One of the things we accomplished is discussing the periodic table, and hopefully you know some vocabulary like period, group, atomic number. Hopefully you have a rough idea of how the periodic table works, where the metals and non-metals are, some of those things. I think that's one thing that hopefully you know. I don't want to assume anything, but hopefully you learned that last year at some point. You're not like brand new to the periodic table, so that's one. The second thing we learned is how to do a task like this. If I were to tell you what subatomic particles there are, it would be nice if you could tell me what we're talking about. Is it an atom or an ion? What is its mass number? What is its name? Right? So quick recap. Its identity and name is based off of protons. Just find out how many protons there are, of course. Its weight, add that to the neutrons. Its ionness, figure out whether or not there's balance or not. Hey, it's Chris. Hey. Perfect timing. Okay, thanks. This is just what I was waiting for. Okay, so here's what we're going to finish off. You guys have 2 things to do to finish off the class. 1, write a reflection now. Okay, give me something I can respond to. I can't talk to all of you guys individually in the time we have left, but write me something about the class. I don't care what it is. Use these questions right here to get you started. You don't have to answer all 5. If I haven't pointed that out yet, I don't need you to literally answer all of these. These are just ideas as to what you can type back to me or talk into your phone. I like doing that. By the way, whenever I respond to you, I'm always talking into my phone, so I'm so sorry that if Google's auto-translate screws it up. So anyways, that's one thing I want you to try. Number 2, you guys can go get textbooks downstairs from the textbook center if you'd like. So why don't we go with this? Go downstairs, get a textbook from the textbook center, and when you come back, try writing a reflection. Does that work? Cool. That worked out just perfectly for timing.